year ago, she came to my office and asked me, well, what should I do to really, get my degree in physics? And knowing her background, and I thought, well, let's find something which really uses both physics and chemistry. And she didn't really know back then how hard this project could be. So after a year or so working on this project, I think really, certainly if you ask her, she can tell you, while the project is full of excitement, it's also fulfilling. She can also tell you often it's very, very challenging. And from time to time, it could be also frustrating. But I keep telling her this is really research, So it's a great pressure actually having Rosie work on this project. So and one time she was kind of like crying in that, and I said, "What's happening?" She said, "Oh no, nothing. It's just allergies." So I took this. So it's just allergies. So here's a Rosie.
Dr. Shi. Like he said, my name is Rosie, and I've been working with him on the fabrication and characterization of titanium or titanium dioxide nanotube arrays. So, like he mentioned, I've been working on this project for a couple of years now. And the initial motivation was I was in this chemistry class where I needed to start some research, and I really wanted to focus on some research that involved both my chemistry and my physics background. So that way I could really just have those fundamental concepts rooted down from the research. So when we first started, we were looking at this paper by Allen and Grimes. And what they were doing is they were forming vertically oriented titanium dioxide nanotube arrays using a fluoride-free aqueous electrolyte. And basically what was so good about this research was that they were using a fluoride-free electrolyte. Fluorides can be very bad for the environment. It's a contaminant, so large quantities is pretty bad. So we really like that they were able to fabricate some of these nanotubes using an electrolyte that didn't contain it. And as you can see here are just some of the pictures of the nanotubes that they fabricated. Just to give you guys an idea of how small a nanotube actually is. If you think of a nanometer, that's about a billionth of 1 meter. So that's about, I'd say about 1,000 times, a little bit more than 1,000 times smaller than the diameter of your hair. So they're very small, and they're very hard to see with the naked eye. You can't see them with the naked eye. So as you can see, their work shows nanotubes, but they weren't very oriented. And that's what we really wanted to do. We wanted to improve on their method to get a very oriented template of these nanotubes. So the method that they used was electrochemical anodization. This is a very straightforward method for the fabrication of these nanotubes. It's an electrochemical process used to produce an oxide layer on a thin titanium surface or a metal surface. It's carried out in an electrolytic cell, which you can see right here. It uses an external power supply, which is connected to 2 electrodes, an anode and a cathode, which become either positively or negatively biased. The anode is really what we're paying attention to. That is the piece of metal that we're trying to oxidize and grow our oxide layer on. So at this electrode, that's where our oxidation reaction actually occurs. We also have an electrolytic cell filled with ions in solution, and that basically just helps conduct the flow of electricity through the circuit to get the reaction to happen. And other than this process being cheap and straightforward, it's also very controllable. So you can either grow a compact oxide layer, which some people do on, metal. Like I know some people will oxidize their guns and that'll turn a certain color, or just any kind of metal, it'll turn in a different color. And it's also a protective layer. So that's more of the compact oxide layer. By tuning the parameters, such as the electrolyzation voltage, the electrolytic composition, the temperature at which you run your reaction, you can actually grow a porous oxide or even an oriented tubular oxide. And that's really what we were focused on in this research. And that's because these oriented nanotubes have a lot of applications they just have a lot of applications, such as photocatalysis. So as you can see here, the pollutants in the air will react with the titanium oxide layer and free radicals will form, and then this will eventually degrade and destroy the bacteria or the pollutants in, for example, like a water source. They can also be used for gas sensing devices. You can put a thin layer on a gas sensor, and this material, when it interacts with the gas, it'll change its resistance very significantly. So as you can see here, when they shoot a little bit of hydrogen gas at the sensor, the resistance drops dramatically. And then as soon as they turn the hydrogen off and shoot it with air, then the resistance goes back up. So it's kind of like an on-off switch. So it's really good if you are trying to monitor a gas leak or something like that. They're also used in photovoltaics or solar cells. They're really good for this application due to their oriented nature and their just orderliness. They have a very good electron transport system because of the nanotube structure. So electrons grabbed from the sun, from photons, can travel down into the circuit of the solar cell. And then there's also other applications such as photoelectrolysis, and they could be used in photochromic devices. There's a lot of applications for these titanium nanotubes. So just to give you a little background of what I've been doing for the last couple semesters, in fall 2014, this is when I really started this project. I was more doing background research, looking at different articles, reading how I wanted to do it, what kind of electrolyte I wanted to use, stuff like this. I was also learning how to use the scanning electron microscope and the energy dispersive X-ray photometer, which I will be talking a little bit more about later. But those are the instruments that I use to analyze and characterize my samples. Then in spring 2015, I attempted to reproduce that work that I mentioned earlier done by Allen and Grimes, in which they used a hydrochloric electrolyte. And during this semester, I kind of found out that I tested all different kinds of concentrations of my HCl. I tried different voltages and everything, and I just couldn't get the nanotubes that I was hoping for. But I was really good at getting a compact oxide layer, which I didn't want. So I kind of decided that the fluoride ions are really important in the fabrication of the titanium nanotubular structures. So from that, we went to the next semester, and we were trying different electrolytic solutions containing a little bit of hydrofluoric acid. And as I mentioned earlier, it is a contaminant. It is bad for the environment. However, we were using a very small amount. Only 0.5% of our solution was hydrofluoric acid, and we reused our solution over and over and over again, so that way we would have less waste produced. And then during this semester, we found that a mixture of monosodium phosphate and hydrofluoric acid was the best electrolyte that would give us our ordered nanotube array. So from then, this semester, we started doing a multi-step anodization process in which we were hoping to increase the order of the array of nanotubes that we were fabricating. So as you can see here, during the first anodization, you get a layer of titanium nanotubes that are pretty disordered. They're not the same sizes, they're just misaligned, things like that. So then, by removing this oxide layer through a process called chemical etching, you can form a template of tiny little dimples on the surface, which will then be a template to start your next anodization. And hopefully this template will force the nanotubes to grow in a more oriented way than they did during the first one. So before you can start your anodization process, you need to prep your samples. And in order to prep your samples, we did a mixture of mechanical polishing and cleaning our titanium substrates. So as you can see here, this is our titanium substrate holder for our polisher. Before, when I first started this project, we were polishing our samples with aluminum oxide polishing paper. So I'd sit there for quite a while, sometimes half an hour to an hour, just rubbing this piece of metal, trying to get all these large bumps and scratches off of it to make it nice and uniform. And it was a little tedious, and my arm was tired at the end of the day, so I didn't really like this process. So we talked to the geology department, and they actually have a nice rock polisher that we decided to use, and that they let us use, which was very nice of them. And if we can we play this video? if you just click on it. This just shows the polisher in work, and what it's doing is it's just removing any large bumps and scratches on the surface. And what was better about thank you. Yeah. What was better about the geology department's polisher was that it was actually able to go to a finer grit than what we had. So we were able to have a much smoother surface. And since we could also do up to 3, which can be cut into 2, so it's up to 6 substrates at once, we would know that all of our substrates had the same starting condition, same starting roughness. So then after we get all those bumps and scratches off the surface, we put it in a bath of methanol and an ultrasonic cleaner, and we just vibrate it until it gets clean. The point of this is to just remove any oils and residues that might be on the metal that might interfere with our reaction. So then we go into the anodization process, and I just wanted to show you some pictures of what I do in my lab. Dr. Shee's lab, sorry. So as I mentioned earlier, we use an electrolytic cell. This is the cell that I've been using. As you can see, I have a platinum wire right here. That's the cathode. It's inert, so it won't mess with our reaction. And then down here in this little part, this is connected to the anode, so this is the anode of the circuit. And basically it's connected to that little piece of metal right there. That's how much of my titanium is actually being anodized during this process. And then I have it on a stir plate just to keep the electrolytic solution agitated during the procedure, just to keep a good flow of ions throughout the whole reaction. And then this is the external power source that it's connected to. I have a resistor in series with the circuit, so that way I can monitor the current with a ammeter, and that just helps assure that the reaction is working the way that I would like it to work. So when you're doing this anodization process, you want to make sure that you're growing your oxide. And there's 3 major ways that you can tell before you go analyze it with the SEM. And so the first one is seen during the reaction. This is the current that I was monitoring. So at first you want to see initial decay in the current. That'll show that an oxide layer is forming because oxide layers are insulators, so the current has a hard time passing through them compared to the metal. So you see an initial decrease in the current. Then as the hydrofluoric acid starts to eat away at the aluminum oxide layer, the layer becomes thinner in certain spots, so there's more current flow. So then you'll see an increase in the current. And then after a while, the oxide growth rate and the dissolution rate will kind of just equal out, and then you're in your steady equilibrium state right here. And this is where hopefully you will get your oxide, your ordered growth of your nanotubes. And then after, when you take it out, just to assure yourself that it actually happened, you can look at your metal, and if it changed color, that means that an oxide layer grew on top of it. And then you could also check the resistance of it, because as I said, it's an insulator. You won't really be able to check, you won't be able to see a current flow through it. So when you check it with a ohmmeter, then you can see that the oxide layer grew, and that, because you'll see no reading here. It will be overload because there's too much. So then after that, you analyze your samples using the scanning electron microscope, or the SEM, and the energy dispersive spectrometer, or the EDS. So basically what the SEM does is it shoots a beam of electrons down at your sample, and then it'll produce an image of your sample on this computer right here, and that's just to see the morphology and the surface of your sample. There's also the EDS part of the instrument, which allows you to look at the elemental composition by shooting a beam of X-rays at your sample, and since each structure has a different atomic structure, then it'll produce different peaks corresponding to what elements are actually in your sample. And this is just a picture of Dr. Shi and I working with the SEM trying to look at some of our samples. So this brings us to some of our results. As I mentioned, we did a multi-step anodization process. So during the first step, these are the nanotubes that we were able to perform. We did it using an applied voltage of 20 volts, the monosodium phosphate and hydrofluoric acid solution, and we did this reaction for about 2 hours. And as you can see, we have a nice array of titanium dioxide nanotubes here. And then just to make sure that it was titanium dioxide, we took an EDS spectrum and found that we did have titanium and oxygen in our sample. So then after that, we etched it using concentrated sulfuric acid that we heated up. It was a little dangerous at first, but you know, hot concentrated acid, it's always fun to work with. And so since it was so concentrated, I only needed to dip my sample into the solution for about 35 seconds. And as soon as I saw the color disappear, I took it out, which indicated that the oxide layer was removed. So then this is just an image of the sample after the etching. You can see that there's just a framework or a template of little dimples on the surface, and we only have titanium left. Then during our second anodization, we used the same parameters as the first, 2 hours, 20 volts, same solution, and we found that we were able to slightly increase the order of the nanotubes. I don't know if you could tell from all the way back there. It's kind of hard to tell when you're close too, but it's definitely a little slightly bit more ordered. And you can see that there's still titanium and oxygen in the sample. And while you would believe that it would be a 2-to-1 ratio of oxygen to titanium, since it's titanium dioxide, we actually see that there's more titanium in the sample just because our oxide layer is very thin, and the X-rays are actually penetrating past the oxide layer into the sample. So that's why there's a higher amount of titanium than oxygen. And this meter right here is about, or this scale bar right here is about 1 micrometer. So these nanopores, I have measured them before, I didn't put that picture up, but they're about roughly 80 nanometers in diameter. And so that just brings us to the conclusions and future work. We were successfully able to fabricate an ordered titanium nanotube array on a thin titanium substrate. As you can see, we were able to increase the orderliness from the work done by Alum and Grimes, so we're really happy about that. However, the degree of order can still be increased for the applications, and that could just be done by tuning the parameters such as the chemical etching time, concentration of that solution, and even the anodization parameters. And I would just like to thank the Department of Physics and Astronomy as well as the Department of Chemistry. I'd like to thank Dr. Shi, because without him I wouldn't be able to have done any of this without asking him for all of his help. Steven Anderson also helped me with the SEM, trying to work that because it's a very tough machine to work sometimes when you're trying to look at things so small. Dr. Sue, he's my chemistry mentor, and the Department of Geology, because they let me use their rock polisher. I'd like to thank my family and friends, the Stepping Up STEM Award and the Source Award for help funding this project. And that's it. Thank you.